Ever pondered about the future of computing technology and the limitations of silicon transistors? The relentless pursuit of smaller, faster, and more powerful computers has driven manufacturers to engineer infinitesimal transistors. Even the most modern processors today play host to tens of billions of these tiny components. But there's a catch. The boundaries of miniaturization are fast approaching. Traditional silicon transistors can only be made so small, often reduced to just a few dozen atoms wide before manufacturing challenges set in. This impending limit has sparked a search for alternative computing technologies. One such example is quantum computers, which, in a departure from the norm, do not rely on silicon transistors. Another emerging field is photonics computing. This technology harnesses the power of light, much like how optical fibers have dethroned copper wires in computer networks. This shift from electricity to light opens up a new realm of possibilities. Now let's dive a bit deeper. Within photonics computing, a team led by Professor Alireza Morandi at the California Institute of Technology is making waves. They're using optical hardware to create cellular automata. These computational models are made up of cells that can live, die, reproduce, and even evolve into multicellular creatures, each exhibiting unique behaviors. Interestingly, these cellular automata are being used for computations, following the path of other alternative computing methods, such as those based on non-living materials. The uniqueness of Morandi's research lies in the realization that cellular automata are ideal for implementation with photonic technologies. They can be perceived as computational models that thrive in light-based environments. Morandi sums it up perfectly. Just as optical fiber can transfer information much faster than copper cable, we're exploring if we can use this information capacity of light for computation instead of just communication. To do this, we're particularly interested in unconventional computing hardware architectures that are more suitable for photonics than digital electronics. The boundaries of silicon transistors are being pushed to their limits, prompting researchers to explore alternative avenues of computing. And that's just the beginning. Stay tuned as we delve deeper into the future of computing technology. Enter the world of photonics computing, an emerging field that uses light instead of electricity. This is a territory where we're not just bending light to our will, but employing it as a fresh medium to carry and process information. Imagine this. A world where the silicon transistors that we've shrunk down to a few dozen atoms wide are replaced by light particles, photons. We're talking about a shift as significant as when optical fibers replaced copper wires in our computer networks, revolutionizing communication speeds and capacity. Now, let's take a forward leap into the fascinating world of Professor Alireza Morandi's lab at the California Institute of Technology, or Caltech. Here, they're not just tinkering with light, they're crafting cellular automata with optical hardware. Cellular automata are computational models made up of cells that can live, die, reproduce, and evolve into multicellular creatures, each boasting its own unique behaviors. These cellular automata aren't just for show, they're used for actual calculations, echoing the trend of other alternative computing methods. But here's the twist. Morandi's team has shown that these cellular automata are more than mere computational models. They're perfect for implementation with photonic technologies. As Morandi puts it, the question is if we can use this information capacity of light for computation instead of just communication. To answer this, they're exploring unconventional computing hardware architectures that are more suitable for photonics than digital electronics. The result? A new breed of hardware designers who are not just harnessing the power of light but using it to perform calculations at light speed. They're transforming images into optical signals, performing complex calculations with specialized chips, and doing it all with improved efficiency and reduced energy consumption. They're slicing the optical spectrum to separate images into different colors and patterns for feature extraction. They're using miniaturized pulsed laser neurons for bio-inspired, unsupervised training. This noise-resilient, energy-efficient approach simulates the behavior of biological neurons. Photonics computing is offering a new horizon where computations are made at the speed of light. Now let's delve into the concept of cellular automata and their role in photonics computing. Imagine a vast grid filled with cells, each either alive or dead, and following simple rules. These cells can live, die, reproduce, and evolve, creating a fascinating dance of complexity from simplicity. This is the world of cellular automata, computational models that are being used to push the boundaries of computing. Prof. Alireza Morandi and his team at the California Institute of Technology are pioneers in this space. They're using cellular automata in conjunction with optical hardware to perform calculations. These aren't your run-of-the-mill calculations, though. We're talking about computations done at the speed of light, harnessing the power of photonics computing. But what makes cellular automata so special for this task? Morandi's work shows that cellular automata are ideal for photonics technologies because they can be seen as computational models. He says, "We can transfer information much faster with light than with traditional means. We're exploring if we can use this light-speed information capacity for computation, not just communication." So, how does this look in practice? In this groundbreaking approach, hardware designers leverage optical processing capabilities. They can transform images into optical signals and perform complex calculations using specialized chips. No more waiting for your computer to catch up with your thoughts. With photonics computing, your hardware is running at the speed of light, making computations more efficient and reducing energy consumption. This isn't just about speed, though. It's about a paradigm shift in how we approach computing, moving away from traditional silicon transistors and embracing the potential of light. By using cellular automata as hardware, we're taking a giant leap forward, making computing more sustainable and efficient. Cellular automata are proving to be the ideal hardware for photonics computing, paving the way for faster and more efficient computations. This is the future of computing, a world where light, not electricity, powers our calculations, and cellular automata are at the heart of it all. In the quest for efficiency, two key strategies have emerged: optical spectrum slicing and the use of miniaturized pulsed laser neurons. Each of these approaches offers a unique set of advantages, pushing the boundaries of what is possible in photonics computing. Let's delve into the first strategy, optical spectrum slicing. This technique involves dissecting images into different colors and patterns. If we think of an image as a complex puzzle, then optical spectrum slicing is like breaking that puzzle down into manageable pieces. By separating the image into distinct components, the hardware can extract features and process information more efficiently. The beauty of this method is that it's scalable and energy efficient, allowing for real-time processing. Imagine a computer that can analyze and process images at the blink of an eye. That's the power of optical spectrum slicing. Moving on to the second strategy, we have the use of miniaturized pulsed laser neurons. This approach takes inspiration from our own biology, simulating the behavior of neurons in the human brain. These pulsed laser neurons can process information rapidly and respond to changes in the input, just like their biological counterparts. This means they can adapt and learn from the data they process, making them ideal for tasks that require learning and adaptation. What's more, this strategy is noise resilient and energy efficient, ensuring reliable performance even in challenging conditions. But what does all this mean in the context of photonics computing? Well, these strategies are not just about processing data faster or using less energy. They are about opening up new possibilities, expanding the capabilities of computers, and bringing us closer to the dream of truly intelligent machines. The combination of optical spectrum slicing and pulsed laser neurons provides a powerful toolkit for harnessing the full potential of light in computing. These strategies are pushing the boundaries of what is possible in photonics computing, offering a glimpse into the future of computing technology. Photonics computing is not only offering new possibilities for computing technology, but is also having a profound impact on artificial intelligence. As we dive into this exciting new era, we're seeing a fusion of photonics computing and advanced data processing techniques that's enabling artificial intelligence to reach new levels of efficiency. Imagine this, computers that can process information at the speed of light. Yes, you heard that right, the speed of light. This is the kind of performance boost we're talking about when we combine photonics with AI. The hardware can transform images into optical signals and perform complex matrix multiplication calculations using specialized chips. This significantly improves efficiency and reduces energy consumption. Two key strategies are driving this revolution. The first is optical spectrum slicing, which separates images into different colors and patterns for feature extraction. This scalable, energy-efficient method allows for real-time processing, a critical requirement for many AI applications. The second strategy involves using miniaturized pulsed laser neurons and unsupervised bio-inspired training. This approach is noise-resilient and energy-efficient, simulating the behavior of biological neurons. It's like we're teaching AI to think more like us, but at a speed we could never match. And the impact? It's far-reaching. AI becomes more capable, more efficient, and more sustainable. It can handle larger and more complex data sets, opening up exciting new possibilities in fields like healthcare, climate modeling, and autonomous vehicles. And as AI continues to evolve, it will only become more integral to our lives, from the devices we use to the way we work. The great news is that with photonics computing, we're not just keeping pace with this evolution, we're driving it. So as we look towards the future of computing technology and artificial intelligence, one thing is clear. The future is bright, and it's being illuminated by the potential of photonics computing. The future of computing technology and artificial intelligence is bright, thanks to the potential of photonics computing.